In this video, we're going to go over the acids and bases chapter from 17.1 to 17.4. So these are the solutions to the in-class activities. The first question we're asking, which is the following has the largest Ka? So the largest equilibrium constant. So remember that equilibrium constant gives us an expression of the products over the reactant. So our reaction is this acid HA dissociating into the H plus and the A minus. So the H would be the little circles here, and the A would be the red dots here that we're representing conceptually. So when that breaks up, it breaks up into the little white circle and the big red circle. So that's how we're showing visually that dissociation of the acid. And remember, the K is the products over the reactant. So that's going to be the proton concentration times the concentration of that conjugate base over the conjugate acid. So this ratio, products over reactants. So the largest Ka, so even though this is a weak acid, it only partially dissociates. The largest Ka will have the most products. So the most of these ions totally separated out. And as we have more products, this numerator gets larger and the denominator gets smaller. So that's going to mean that the Ka gets larger. So if we look at this Ka, we've got two of the A minuses, two of the protons, and we've also got two of the HAs that stay together. So that weak acid that stays together in undissociated form. So that has a Ka of 2. And in this one, we have even fewer dissociated. We only have one dissociated. So we were to calculate that Ka, 1 times 1 divided by 3, so 0.33. And in the third one, we only have one of the H's, one of the weak acids together. 3 of them have dissociated. So the 3 times the 3 divided by the 1 equals 9. So this would give us the largest Ka value. Now let's go on to problem number 2. So problem number 2, we're looking for the Arrhenius acid. And remember, we define acids in 3 ways. There's the first, most basic definition, the Arrhenius, which is the definition that most people learn at the beginning of learning about acids and bases. But the Arrhenius produces H plus in water, and the base produces OH in water. And the Bronsted-Lowry, we have a proton donor and a proton acceptor. So we had to use this definition to account for how ammonia works and making ammonium hydroxide as we transfer the proton. And then the Lewis definition, we're going to talk more about when we look at transition metals. But if you're having trouble remembering these definitions, so the Arrhenius one has the H in the Arrhenius, and it produces H plus in water and produces the OH in water for the base. So that's how some students like to remember this. And the Bronsted-Lowry, the Bronsted has the T in it, and that T looks like the positive sign, like the H plus donor and the H plus acceptor. And then the Lewis has the E in it for the electron pair acceptor and electron pair donor. But we're looking for the Arrhenius acid. So that Arrhenius acid produces H plus in water. So typically when we look at these acids, they'll have the H written out in front. And if we look at this formula for sulfuric acid, we have those 2 acidic protons written out in front. So those will produce the H plus ions when dissolved in water. If we look at the other options, lithium hydroxide, this is the Arrhenius base. Remember that OH is attached to or ionically bound to the alkali metal. So this is an ionic interaction, so that OH is basic. And then with CH3, they're all carbon-hydrogen bonds. It's all covalent bonding, so it's not an acid or a base. And then for the last one, if we draw out the Lewis dot structure for this nitrogen here, so we'd see the 2 hydrogens bound to it and a nitrogen carbon bond, and there would be a lone pair on the nitrogen. So that lone pair on the nitrogen makes it a Lewis base that has lone pairs. They also accept the proton ion. So this would also be a Bronsted-Lowry base as well. Now in 3, we're looking for the Arrhenius base. So if we go through the options here, we're looking for an OH to be written after a metal or polyatomic cation in the formula. So in the first option, we've got lithium chloride, so that's an ionic salt, it's neutral. The second one, we have CH3OH, so that OH is bound to a carbon, so this makes this an alcohol. So in this case, that OH, it's not a hydroxide, it's an alcohol because it's attached to a carbon. But with C, the OH is attached to that metal, so either a metal or a polyatomic cation, and that's going to make this a base. And then D, we have C, double bonded O, single bond to the oxygen, and then a single bond to a hydrogen. So it looks like it has the OH in it, but it has a COOH. And remember that COOH functional group, whenever it's attached to a carbon, that's a carboxylic acid. So that's a weak acid. So that's something we've just got to remember. But this is how we're getting C for that answer. Okay, so let's go on to question 4. We're looking for the Bronsted-Lowry acid. So in this case, the NH4 plus, this is the conjugate acid of the ammonia. So it's got a proton that it can donate. So it's already positively charged. It's got an extra proton than the neutral ammonia. So we can think of this as a Bronsted-Lowry acid. So this NH2 minus, it's already negatively charged. It's unlikely to give up another proton that's just positive charge and become even more negative. And then with CH4, those carbon hydrogen bonds, there's strong bonds that are unlikely to break because it's not polar, it's totally covalent, and there's no lone pairs. The Br2 covalent compound, non-polar covalent, has lone pairs, but it doesn't have any protons to transfer. And then because you've got the lone pair on the nitrogen here of ammonia, it's more likely to accept the protons than it is to give up. So the NH3 is the conjugate base, the NH4 plus is the conjugate acid. But since it's going to be a proton donor, this is why we classify it as a Bronsted-Lowry acid. Now in 5, we're looking for which of the following species is amphoteric. So AMP, so it acts like an acid or a base depending on its environment, and it accepts or donates a proton. So think of that AMP like amphibian. So it lives on both the land and water. So this compound can act like an acid or it can act like a base depending upon its environment. So I'm going to draw the Lewis dot structures of each of these compounds. So we've got the CO3, 2 minus. So there's no hydrogens, protons available to donate. So this can't be an acid. If we look at the HPO4 2 minus, we've got a proton on the hydroxide here, and this is a hydroxy acid, also an oxy acid. So that proton is acidic because that oxygen is pulling electron density from that hydrogen. And also you've got the electron density being pulled away from the other oxygens here from the phosphorus. So that weakens that bond here. So this proton is acidic, but also too, you've got this negatively charged oxygen here. So if there was another proton available, it could add to the lone pair here to cancel out that negative charge. So in this case, the HPO4 2 minus would be amphoteric. Now looking at HF, so that has a acidic proton to give off, but it is not a base. It's not going to accept another proton. And then the NH4, so yes, it has an acidic proton to give away, but it has no availability to take on another proton because its valence shell is completely full. So of our options, that HPO4 2- is our best option for the amphoteric. And in question 6, we're asked, what is the conjugate acid of the bicarbonate ion, so HCO3-. So if we're looking for the conjugate acid, this must be the conjugate base. And remember, conjugate acids and bases only differ by a proton. So this is the structure of the HCO3. So if this is the conjugate base and we want to know the conjugate acid, so we need to add another proton to that. Because remember, a conjugate acid base pair, so if this is the acid, this is one with the base with the proton removed. And if this is the base, the NH3, if we add a proton, we have NH4, so that's the conjugate acid. So if we're looking for the conjugate acid of this base, we need to add a proton. So that's how we get the H2CO3. So if we think of the HCO3 as being amphoteric, it could lose another proton, and its conjugate base would be the HCO3 2-. But they ask us for the conjugate acid. Okay, so 7, which of the following is not a conjugate acid base pair? So remember, those conjugate acid base pairs only differ by a proton. So NH3, if we add a proton to it, makes it NH4 plus. So we've added another hydrogen and we've added the plus charge. If we add a proton to the HSO3-, we get another hydrogen and we lose that negative charge. If we take the C2H3O2- here, we add the hydrogen. So we've got the hydrogen here, we add the plus. So the plus cancels out the negative charge, so we're neutral over here. So A, B, and C are all conjugate acid base pairs. Now going to D, if we add an H plus to the OH- here, that would give me water. So H2O neutral. But to get to the H3O plus, I'd have to add 2 equivalents of the protons from the hydroxide. So that's not a conjugate acid base pair. There's an intermediate in there, the water. So remember that conjugate acid base pair can only differ by 1 proton. Now question 8, we're asked to identify the weak diprotic acid. So weak, if it's not one of the 6 strong acids that we were asked to memorize, we know it's weak, or if they give us a Ka, that's another indication that it's weak. But also to the di part, the di means 2. So 2 protons in the acid. So just by knowing the definition of diprotic, we can exclude A, because this is monoprotic. B is also monoprotic. C is diprotic, so C, we'll have to come back to this. D is triprotic, because there's 3. E is diprotic as well. So C and E are both diprotic, but we need to figure out which one is the weak. And we have memorized that sulfuric acid is one of our strong acids. So strong completely dissociates. That first proton completely dissociates in H2SO4. So this is a strong acid, but H2SO3, that sulfurous acid, is weak. And I'm just showing you here the titration curve of a diprotic acid. So they're going to have 2 of these inflection points. So this is where the first proton is neutralized. So here we're adding volume of base, and this is the pH. And then you have this other sharp increase in the pH once that second proton is removed. So this is just a titration curve showing you how you find out if something is a diprotic acid. So you should have 2 of these regions where you have these sharp increases in pH. Now the 6 strong acids that we ask you to memorize. So perchloric acid. So that's one of those oxyacids, nitric acid, and sulfuric. And then the other ones, these are, if you just go down the halogens, but remember HF is a weak acid. So then it's hydrochloric, hydrobromic, and hydroiodic. Those are all our strong acids. So sulfuric acid is listed here. Sulfurous is not listed on this list. So that's how we know C is our correct answer. Then in 9, the question, the stronger the acid, then which of the statements below is true? So there's this inverse relationship between the conjugate base and the conjugate acid. So they're a weak system. So, but even though they're both weak, one is going to be stronger than the other. And the stronger one is, the weaker the other. So the stronger the conjugate, the stronger the acid, then the weaker the conjugate base. So that's going to be a very important concept for us to understand. Now in 10, they want us to give the characteristics of a strong acid. So remember, a strong acid completely dissociates in water. So we're saying this HA acid, so this generic acid here. So once we put it in the water, all of it breaks up. So all of it has been converted into the hydronium or the H+, and then the anion of the acid. So remember, these are our 6 strong acids. And so here's just an example of nitric acid. And nitric acid is an oxyacid. So the strong acids don't necessarily have to have an oxygen attached to them, but many of them do. So like the nitric and the sulfuric and the perchloric acid. But if we also look at the other options that they give us, it's going to have a weaker bond to the hydrogen. Because what happens if you, like in the HCl, the chlorine is very electronegative. It pulls most of the electron density towards the chlorine and really polarizes that bond. And so that weakens that hydrogen chloride bond. So you're more likely to lose the hydrogen as a proton. Also too, when you have these oxyacids, so like nitric acid, you've got the nitrogen in the center, and you've got these 3 oxygens around, which are very electronegative. They're pulling electron density away from the nitrogen. So the nitrogen is very electron deficient. So this oxygen here is pulling electron density here, but it's also competing with these other 2 oxygens. But it's also attached to this hydrogen. So there's this net pull of electron density from this hydrogen that weakens this bond. So it weakens that bond. It makes this bond very polar in that process. But also too, we said that the strong acids ionize completely. So B, C, and D are always true. A is true most of the time. So this is why the best choice for this question would be E, all of the above. Now in question 11, they're asking which of the following is a weak acid. So remember, weak acids, so here's an acid here. When we look at it, when it goes into solution, most of it stays together and some of it dissociates. So notice that we have most of our HAs together here. And then on this side, all those HAs, they're all completely dissociated for the strong case. But the weak, we have very little here. So we're going through our list. If it's not one of the 6 strong acids we were asked to memorize, it's weak. Nitric acid is strong. Perchloric acid is strong. Hydrochloric acid is strong. Sulfuric acid is strong. And this acid is not listed on our list. And also too, we have this COOH. So that's a carboxylic acid. So that's also weak. So this is how we know E is a weak acid.